Welcome back to the Deep Dive. We have pulled together your sources, articles, and research on one of the most deceptively simple, yet utterly critical pieces of software in the modern tech world. Today, we are cracking open the essential, the invisible engine behind almost all modern data science and machine learning in Python, Numpy. Our mission is to distill the core functionality, the sometimes confusing terminology, and most importantly, why this library is a shortcut to being a truly high-performance data scientist. And the crucial fact to start with is just .speed. What you really need to know about NumPy is that it is a Python library built specifically for fast array computing. And when we say fast, we mean it operates at the speed of highly optimized traditional languages like C and Fortran.
And that speed is so critical because of the sheer scope of functionality that's built on top of it. I mean, NumPy offers everything: comprehensive mathematical functions, powerful random number generators, all the way to sophisticated linear algebra routines and Fourier transforms. It's really the toolbox for all the heavy lifting. But the real reason we're dedicating a deep dive to it is its foundational role. If you work in data, you are using packages like Pandas, SciPy, Matplotlib, scikit-learn.
All of them.
Every single one. And they aren't just built on general Python, they were built directly on top of NumPy. Without it, the scientific Python ecosystem as we know it, well, it just grinds to a halt.
Okay, so let's unpack this core question because I think this is what separates the casual Python coder from the data professional. Python already has lists.
Yep.
Lists are incredibly flexible. You can put anything in them: numbers, strings, even other lists. So if I make a list of, say, 1 million integers, why do I need to convert it to a NumPy array to get speed? I mean, if it's all the same type, shouldn't a Python list be fast enough?
That is the best possible question, and it gets right to the heart of computer science efficiency. The crucial distinction is memory architecture. Your standard Python list is heterogeneous. That just means it allows for mixed data types. The actual data structure isn't a solid block of memory, it's an array of pointers.
Pointers, so like addresses.
Exactly. Each pointer just points to a separate Python object somewhere else in memory, and that object contains the data type, the value, all that other stuff. And that flexibility, it comes at a huge cost. When Python iterates through that list, it has to chase all those scattered pointers, check the data type of each object, and then perform the operation. It's slow, and it's very inefficient for the CPU's cache.
So the CPU has to jump all over memory just to figure out what it's looking at every single time. It's like having a filing cabinet where the folders are labeled, but the actual contents are stored in a random warehouse across town.
That's a perfect analogy, exactly. Now, compare that to NumPy arrays. They are strictly homogeneous. Every single element must have the same type, which we call the array's D-type. Because of that uniformity, NumPy can allocate one single contiguous block of memory for the entire array. The underlying C code knows exactly where the banner starts and knows every item is, say, an 8-byte float, and they are all lined up perfectly next to each other. It doesn't need to check types or chase pointers. It just streams the data, and that's what gives you that exponential speed game.
That dramatically clarifies it. The uniformity cuts down on all that overhead. So now we understand why it exists. Let's focus on the heart of the library. The central data structure, the end array.
The n-dimensional array.
Right.
Okay.
And for you, the listener, the good news is that creating one is simple. You can just take a standard Python list and turn it into an end array using np.array.
But once you're in the NumPy world, we do need to talk about structure, because this is where a lot of people get tangled up. The end array is defined by some specialized terminology.
Let's break it down.
Okay, let's start with shape. The shape is just a tuple of integers that tells you the size of the array along each dimension. So a shape of 3, 4 means
3 rows and 4 columns.
Exactly. Then you have rank, which is even simpler. It's just the total number of dimensions. A 2D matrix has a rank of 2.
And crucially, we need to clarify what the dimensions themselves are actually called. In NumPy, they are called axes.
Right. And this term can be confusing. We usually think of x and y axes in a plot. But in NumPy, an axis is just a dimension. In that 2D matrix, the first axis, axis 0, is the row. The second, axis 1, is the column.
And if you had a 3D tensor, like for image data, axis 2 might be the color channels or something?
Precisely. It's a framework for how the data is indexed.
So to clarify the common names you'll hear all the time in data science, a 1D array is a vector.
Yep.
A 2D array is a matrix. That's your standard table of data.
Right.
And anything 3D and higher, things like data cubes or neural network weights, those are just called tensors. And it's vital to remember, the array is a fixed size container. You can't change its type after you create it.
So now that we know how the data is organized for speed, let's talk about the operations that really use this structure. And we have to start with the biggest time saver of all, broadcasting.
Broadcasting is one of those concepts that sounds abstract, but you use it, every single day.
Yeah.
When you do basic math between two NumPy arrays, you're doing it element-wise.
Right, they have to have compatible shapes. AI plus by.
But what happens when the shapes don't match? Specifically when you have a big array and just a single number.
Well, that's broadcasting. It's NumPy's internal mechanic for handling arithmetic between arrays of different shapes, and it does it in a highly efficient way. So imagine you have an array of, say, 10,000 prices in a catalog. You need to apply a 10% tax to every single one.
Okay.
Instead of writing a Python loop that iterates 10,000 times, you just write price array 1.10.
And that 1.10, that's just a scalar, a single value.
Correct. And NumPy doesn't physically duplicate that scalar 10,000 times in memory. That would be wasteful. Instead, broadcasting creates a virtual array behind the scenes. It sort of stretches the scalar across the whole price array and does the multiplication instantly.
So it saves a huge amount of memory and time by avoiding those slow, explicit loops.
It's pure magic.
Okay, so if the data is organized for C speed and the operations use this virtual memory trick, where does this take us in complex computing? Because, data science isn't just adding a tax to a list.
It leads us directly to linear algebra. The whole purpose of the array structure is to enable lightning-fast matrix computations, and those are the backbone of virtually every machine learning algorithm.
From basic regressions to huge neural networks.
Every single one. And the specific function you have to know is the dot product, the matrix multiplication. In pure Python, writing a fast dot product is a nightmare. In NumPy, it's one highly optimized function, np.dot. Or even simpler, you can just use the add operator now. This lets you multiply a, say, 100 by 50 feature matrix by a 50 by 1 weight vector with incredible speed. Without that, training a large model would take weeks, not hours.
That's a powerful connection. NumPy is basically the reason deep learning is even feasible today. And beyond the fundamental math, let's quickly look at control. We mentioned earlier that NumPy lets you precisely control operations. Let's take sorting an array.
Absolutely. The capability is what matters. When you call np.sort, you can tell it which axis to sort along. Maybe you only want to sort the rows but leave the columns alone.
And you can even specify the algorithm.
Exactly. You have options like quicksort, merge sort, heap sort, and you might ask, why does that matter? Well, depending on your data size and memory, different algorithms have different performance. NumPy gives you the steering wheel to optimize that.
That's a huge sign that this isn't just a basic tool. It's a dedicated scientific platform.
And if we connect all of this to the bigger picture, the combination of that C speed, the memory layout, and advanced features like broadcasting, that's what makes scientific modeling a real-world possibility.
Let's make this concrete with the ultimate example, the mean square error, or MSE. If you're training any predictive model, you absolutely need this metric to see how far off your predictions are.
Right. The mean square error is calculated with this formula. You take the sum of the square differences between the predicted and actual values, and then you divide by the number of predictions.
It looks complicated on paper.
It does, but we can break down that complex formula into simple vector-level operations in NumPy. That's the magic.
So walk us through it step by step.
Okay, you start with U prediction dollars and dollars. Both are just huge vectors of values. The first step is the difference. In NumPy, that's just one line, U prediction Y.
And that subtraction happens instantly across potentially millions of data points.
Instantly. Next up, the squaring operation. Again, in NumPy, this is just the difference too. It's an element-wise operation, so every single difference is squared in one blazing fast C operation. No loops.
And finally, the big summation symbol, that sigma, and the division by null.
The summation and division are just two more optimized NumPy functions, np.sum and np.mean. You sum the squared errors, and then you can just call the mean function to divide by null.
So what would be multiple nested loops and massive overhead in pure Python?
Is executed in 3 simple, readable lines of code at the speed of C. That is the fundamental reason machine learning works today.
It really is the ultimate shortcut to performance. So what does this all mean for you, the learner? Let's summarize the key takeaways. NumPy is your direct shortcut to C and Fortran speed right in Python, and it's all enabled by one single architectural choice, that core homogeneous data structure, the end array.
Which ensures your data is stored in one contiguous cache-friendly block of memory.
Remember that the array defines its size through its shape, and its dimensions are called axes.
And because that rigid structure is in place, it enables those high-efficiency features like broadcasting and, of course, the core linear algebra capabilities you need for any serious data work.
So we've seen how foundational Numpy is. I mean, it underpins the entire data stack. Yet its core performance relies entirely on code written in C and Fortran. It's an elegant layer of abstraction.
And this raises a really important question that I think defines modern data engineering. Think about this layering, where the fastest parts of your software are actually built using these older, highly optimized languages. How does knowing that the engine driving your favorite Python library isn't actually Python change how you approach learning new high-level libraries built on top of it, like pandas or SciPy?
That's a really interesting thought.
That mindset shift, I think, is what will define your career in data science.
We'll catch you on the next deep dive.